Swayam Prabha. Digital India. Educated India.
So, in the previous class, I discussed some of the techniques for characterization of particle clusters in turbulent flows. So, we have seen different techniques, and that includes particles in a box counting approach. Then we have the approach of radial distribution function, and then Voronoi analysis. So, in Voronoi analysis, it is the results are unique in the sense that we are able to characterize the particle clusters in instantaneous images. Okay. So, and then once we identify the clusters, then we can characterize the clusters, we can measure the area, the length associated with it, and also the local number density within clusters, as well as all these parameters can be calculated as well as in the voids. Apart from that, the application of Voronoi analysis facilitates calculation of many other quantities, as I will discuss now. So, one of the important quantities is interparticle spacing. Okay, so this is basically, we know that this is inversely related to the local particle concentration. However, this quantity itself is of interest. So, this is calculated by using the Delannoy triangulation method. So, in this case, the intention is to calculate the average interseparation distance in each cluster. So, here what has been observed is that within a cluster, the separation distance does not vary much. So, we can calculate or we can define one average interseparation distance for each cluster which is measured at a time instant, at one time instant. So, this Delannoy triangulation is basically, it corresponds to the Voronoi cells only. So, if you basically connect all the nodes in a Voronoi cell, as you can see here, the nodes here means the particle position. So, if you connect a particle to, or connect one node to the neighboring nodes, so such that you connect only those cells which share a boundary. So, for instance, if we consider this cell, for example, you can connect to this node to this one, this one, this one, this and this. So, you connect the nodes to only to those cells or nodes of those cells which share a boundary. And these actually define the actual neighboring particles around a test particle. Because now let us say you have an image and you have identified some particles here. Now, the question is, how do we define interparticle separation distance? At first sight, it may seem to be very straightforward, but if you see, it is not. For instance, let's consider this particle. So, how do we calculate the interseparation distance for this particle? So, which will be the interseparation distance? Because you can calculate the separation distance between this particle and all of the remaining particles. So, how will you define which should be the actual neighbor of this test particle? Okay. So, the Delannoy triangulation method gives us one way to identify those, and this is done by this way. For example, in this case, we have these droplets in the cluster, and through Delannoy triangulation, we can get the we can connect the particles to the nearest neighboring cells, and that is how we get these lines. And if we average all these lines, we get one characteristic spacing. And we can do this now for all the clusters that we have. And what is interesting is that we get a distribution. So, these results correspond to, say, for example, this red color symbols, they corresponds to one location in the spray. So, what you see here is that the separation distance in the clusters of different size itself is not same. Within a cluster, we can assume that the separation distance are more or less same. But if we compare that average separation distance between or among different clusters, they are not same. In fact, we see a distribution of the particle separation distance. So, in this case, the separation distance has been normalized by the particle or average particle size or average droplet size. So, you see that the separation distance can range, for instance, from 2 to about 30-40. So, the separation distance between particles can vary from 2 times the particle size to 40 times the particle size. So, this means that within a cluster, the concentration can vary. So, the local concentration in different clusters may vary. It depends on the size of the cluster. Okay. And we do that for, in this case, for different locations downstream of the injector exit. So, Z is equal to 30 means this is, in this experiment, this is closest to the injector. Then at 45 and at 60, and you see that as you move downstream of the injector exit, then you see that the average cluster separation distance, which is given by, you can say, this peak of the distribution, this shifts towards right. This means that particle spacing is increasing as we move down, which is expected. However, there is always a distribution and the distributions may overlap. But here we see that the on average it changes from about 10 times the particle size to about 100 times the particle size. This is a log scale. Okay. So, all this information we can get. Next, the Voronoi analysis also facilitates measurement of group number. So, we have already discussed what is group number. So, this is a non-dimensional number that tells us the extent of group gasification of droplets, and this number is basically a geometric parameter of a droplet cloud. So, in this case, we treat the cluster as a cloud of droplet. So, this number depends on particle size, the average size of the particles or droplets, and it depends on the separation distance between the particles, and it depends on the size of the cloud, or in this case size of the clusters. And you see now from Voronoi analysis we have these information, and if we can combine this with some size measurement, let us say from eyelids, then we have all the parameters required to calculate this group number, and that is what is done here, as you can see in the complete flow chart. So, here we have a PIV image, and we do Voronoi analysis, and we also do Delannoy triangulation to calculate the separation distance, then the length scale of the cluster. These are different length scales. So, in this case, if you define major and minor axis for each cluster instead of a circle equivalent size, then you will get this expression, and we need also the average size of the particles or droplets, which we can get from eyelids or any other technique. But in this case, the measurements have been taken at the same location using PIV and eyelids both. So, that is why this gives also the local size. But and finally, you calculate the group number. Okay. But we have to keep in mind that here what is assumed that in all these clusters the average size is given by the overall arithmetic mean diameter that you get from the eyelids image. I hope it is clear. So, here we do not have information about the size of the particles in individual clusters, because we are using another technique to measure the size. We do not use Voronoi technique to measure size. Voronoi technique is only based on the particle position, that is all, not size. So, anyway, we can calculate, or we can, I would say, we can estimate group number like this, and in the spray, in the same spray that we just discussed, where I have shown the results for the PDF of the interseparation distance, for those locations now we can calculate the group number, as you can see here. So, this is the group number which is calculated for individual clusters. So, you see that you have a distribution of the group number. So, basically the group number itself is not same, it depends on a particular cluster, it depends on the size separation distance of the droplets of that cluster. And what is interesting here is that for all cases you see that the group number is not unique, the group number itself varies from over a wide range from 0.1 to 10. This, if you remember, we have discussed what is the significance of the magnitude of this group number. If this group number is much below 1, then we have more like isolated droplet evaporation or combustion. But if the group number is of the order of 1, then we have internal group evaporation, and if it is more than 1, much more than 1, then we have external group evaporation, which means that you have a dense cloud of droplets where evaporation can even stop within the core part of the cloud. So, what is interesting here is that you see all of these modes are present. So, basically here we have multi-mode group evaporation or gasification going on. And if you see this curve, this shifts towards left, that is towards smaller group number as you move downstream of the injector, which is making sense, because as you move away, the particles are far away, so they tend to evaporate or gasify individually, and that is the reason why it shifts towards left. But still, even then you see that even below 60 centimeter, that is half a meter downstream, more than half a meter downstream of the injector exit, you see that there are some clusters where the group number is of the order of 1. But so, this means that even far away from the injector exit, the droplets may not burn or may not evaporate individually always. Okay, so, that is what is interesting. Okay, so, finally, there is, as I just mentioned, if we use Voronoi analysis of the PIV, then we can identify and characterize clusters, but we do not know what is the size distribution in clusters. So, that is why we developed a method by applying Voronoi analysis to the eyelids images, because in eyelids image now, you not only get the position of the particles or droplets, but also you know the size of individual droplets here. So, now if we do Voronoi analysis to this, then we know which are clusters, and now we know what is the size in clusters, and that is what was done. And here you can see the difference in the size distribution in this. So, this shows the droplet size distribution in voids and in clusters, and you see that they are not same. So, there is some difference. So, what we see here is that the probability of smaller size droplets are higher in the cluster, and the probability of larger size droplets is lower in the cluster. So, basically what happens, the characteristic size or say SMD actually reduces in clusters. In this example, again these are not universal, in this experiment what we have seen is that in the spray, as we move, so here it shows the radial profile of SMD. So, here you see for all cases there is some change in the SMD as you move from the center of the spray towards the edge of the spray. But what is interesting is this comparison. So, this black dot shows the overall SMD, that is you get from eyelids directly, but this gives you the size of the clusters only. So, this is conditional measurement. So, conditional on clusters or voids, you can measure the size of the droplets, and what we see is that here we have larger droplets in the void and smaller droplets in the cluster. So, this means that clustering causes, not only clustering is due to preferential accumulation, but there is preferential segregation of droplet size also. Although the difference here you see is not significant, but it is consistent. So, it is about say 20% of the size that we measure, and this is consistently observed at all locations. Okay. So, this is a novel application, but considering that the applicability of eyelids technique is only for dilute sprays. So, you can use this technique or Voronoi analysis of eyelids images only for dilute loading. So, finally, there are some limitations of Voronoi analysis also. So, this is a common limitation in all 2D measurements, that we have projection of the particle position. Actually, we have clusters in 3 dimensions, but when we take 2D imaging using a laser sheet, what we get is 2D projection of 3D particle distribution. So, the Voronoi cells represents projected areas, not true 3D volumes. However, the same technique can be used to if we have 3D measurements. The other problem is that the Voronoi analysis is not sensitive to the particle shape or size. Whatever is the particle size, what it needs is only the particle location. So, the effect of particle size it is not possible to include here. And also importantly, subsampling as a consequence of intensity thresholding for identifying particles can influence the result to some extent. So, as I have already discussed, so in case of laser sheet imaging or in case of any 2D imaging, we do not identify all the particles, because you have to put some intensity cutoff to identify the particles, and the particle intensity will depend not only its size, but its position within the laser sheet, which is Gaussian. So, a small particle which is lying towards edge of the sheet will have smaller intensity. So, we will tend to reject it or filter it out, while we will always pick up larger particles. So, this problem itself can cause some bias. However, we have seen that, so as you can see here, how this PDF of the Voronoi cell areas changes as we change the intensity cutoff. So, you choose some optimum intensity cutoff, this is given by this parameter beta, and then we change the intensity thresholding. So, we increase it, we decrease it, and you see how the Voronoi cell area is affected, and you see that mostly the small scale cluster probability changes, but the change is small. And also how the degree of clustering changes as you change this beta value. So, you see that more or less it is constant. You see some differences when the mass loading is high. So, this means that if you have dilute loading, it will not affect much, but if you have high loading, so you see there is some difference here, you see. However, this difference itself is very small. So, finally, in spite of these limitations, Voronoi analysis remains as a powerful and elegant method for quantifying clustering and local spatial structure of the clusters. So, here we end this topic. We will move on to the next topic, which is the final topic of this module. and we will briefly discuss particle-particle collisions in multiphase flows. So, as of now, we have always avoided particle collision because obviously it brings in more complexity. However, it is important to understand particle collisions in multiphase flows, mainly because we can neglect particle collisions only when we have dilute flows, typically if the particle volume fraction is less than 10 to the power of minus 3. So, in that case we can have very dilute flows where the volume fraction is below 10 to the power minus 6 or 10 to the power minus 6 to 10 to the power minus 3, where we have two-way coupling, but the collision is not important. But it can be shown that when we have volume fraction of the order of 10 to the power minus 3, then collision become more frequent, as in these examples. For example, sprays especially close to the injector exit, fluidized beds, aerosols, dust explosions, cloud microphysics. So, in all these cases collision plays a very important role in the evolution of the particles. So, as the particle concentration becomes higher, particles collide with each other, then the loss of particle kinetic energy due to interparticle collision cannot be neglected. And we should remember that particle collision may change size and number density. They may lead to shattering of particles, generating more particles, smaller particles, or two particles can combine and coalesce. This may or may not happen, but what is bound to happen is change in velocity. When two particles collide, even if no new particles are generated or consumed, or particles are consumed, means the number will decrease in case of coalescence, but the velocity will always change. Mostly the velocity will change. So, in multiphase flow dynamics, we have two different phenomena where particle-particle interaction are important. One is collision dominated flows, where you see now the loading. So, this case now we are dividing that into two parts. One is collision dominated flows, for example, say in sprays, where the volume fraction is between 10 to the power minus 3 to 0.1. And then we have contact dominated flows. Contact dominated flows means the particle-particle contact time is more, as in the case of fluidized beds. So, now, but what is the difference? If you see in both cases you have particle-particle interaction, but the time scale is only different. So, in case of collisions, here we have very short contact time, but this causes entirely different modeling approach for collision dominated and contact dominated flows. So, accordingly we have two different modeling approaches. One is hard sphere model, which is suitable for collision dominated flows, and the other one is soft sphere model, which is essential for contact dominated flows, though we can use this for collision dominated flow also. So, in case of hard sphere model, the collisions are binary and instantaneous, and temporal evolution is not resolved, which is suitable for collision dominated flows. So, what is meant by this is that you need to know only the outcome of the collision. If two particles collide, what is the outcome? So, let us say the outcome is coalescence. Then in your model you specify what are the inputs required. So, in this case say particle size, particle velocity, and the output what happens. So, if let us say it always leads to coalescence, then accordingly you consider the mass conservation. You say that okay, now instead of two particles I have one particle with larger mass, and the velocity also changes accordingly. But you do not model this process, how this is happening. So, that is what is hard sphere model. So, you directly model the outcome and implement, but in case of soft sphere model, you consider this entire process of collision, how two particles come. So, when two particles approach each other, what happens is that the gas between the two particles, if you have gas solid flows or gas liquid flows, or say the carrier phase within the two particles is compressed and the local pressure actually rises. So, whether the particles, if collision happens, then what will happen, whether they will just bounce back or they will coalesce and deform again, it depends on that phenomena basically. Okay. So, from what we have studied earlier, that is Lagrangian tracking of particles or droplets. Okay, we have discussed this. So, the question is, how do we implement these models here? Okay. So, mainly we will confine our discussion to hard sphere model. So, in Lagrangian droplet parcel concept, we have only point masses which are tracked. So, we have already discussed this, I am again not going into detail. So, there are two ways. One, in the Lagrangian tracking itself, there are two ways. One is you actually resolve the flow around, fully resolved flow, you resolve the flow around particles. The other approach which is mostly used is the point particle assumption, that is you do not consider the physical presence of the particle, but you account for all the forces. So, now in that case you have basically 2 points. So, now how do you model the collision effect? So, in this case again, as I mentioned here, this basically refers to hard sphere model, and in this case the collisions are treated as binary and quasi instantaneous, which means almost instantaneous. Now, in order to ensure that during a Lagrangian tracking time step only binary collision can occur, the Lagrangian time step needs to be smaller than the reciprocal of collision frequency. So, basically your time step should be smaller than the collision time scale, then only it makes sense to model. So, the time that it requires for the outcome to happen, two particles came and they collided and let us say they coalesce. Now, it requires some time. Now, this time should be much smaller than the intercollision time. Okay. That is, this time should be smaller than the time that the particle would need to collide with another particle. Okay. And also your time step in your simulation. So, now at this point you would have heard about this term binary collision. Why we are invoking binary collision always? So, it is important to understand what is meant by binary collision. So, basically in collision dominated flows, the probability of 3 particles, 3 or more particles actually being within a collision volume simultaneously is very small. So, it is a rare event that we have more than 2 particles colliding with each other in collision dominated flows, that is when you have volume fraction below 0.1. So, these are not contact dominated, these are collision dominated flows. So, that is why binary collisions dominate this system mostly. So, binary collision means we have collision between 2 particles only. So, accordingly many people have studied this, and this is an example of an experimental setup which is used for imaging binary droplet collision events. So, here you see there are 2 droplet generators. So, these droplet generators generate a very simplified spray. Simplified spray means it will generate only a stream of mono-sized droplets. So, that is why it is ideal to do fundamental studies like this. So, here they have taken 2 droplet generators and they have inclined it, and they allow the droplets to interact with each other. and then we can change the droplet size, we can change the droplet velocity, we can change also the angle between them, and we can look at the outcome of the collision using a high speed camera. So, by this way we can understand the complex systems as a superposition of binary events. So, basically we can say that many binary events are taking place, and finally what we see is a combination of all these binary collisions. And this is very important for model development and validation of simulations. So, what are the factors which influence the outcome of binary particle collision? Which factors influence the collision process? So, here you can see two particles are coming together and they are just in touch with each other. So, the collision process is just starting. So, obviously here the size of the particles are important and also their velocity. Now, it is the relative velocity which is important here, which dictates this collision process. How do we define relative velocity? This is, if we know the individual velocity, we can calculate the relative velocity as vector sum of the individual velocity. Then there is a very important parameter called impact parameter. So, now the outcome of the collision would depend on how they are approaching each other. For instance, if two droplets are just heading on to each other, or they are just kind of grazing. So, it is like this. So, that is why we have defined this parameter called impact parameter. So, it is not only the relative velocity, but also the impact parameter, which is basically a normalized orthogonal distance. So, this parameter B is normalized by the average size of the two particles. So, if the particle size is same, then here this is the size of the particle in the denominator. Now, what is B is basically, here you can see this is B. So, you know what is the relative velocity. So, you draw the relative velocity at the center of one particle, any of these two, does not matter. You draw this relative velocity at the center of this particle, and then you calculate the normal distance from the other particle to the relative velocity. So, this one, I hope this is clear. So, this is your relative velocity and this is the normal to the relative velocity from the other particle. So, this is the distance B, and you normalize that with the average particle size. So, when we have B is equal to 0, so you can imagine how B can be 0. If the B value will be 0, if the two particles approach this way, and B is equal to 1 means grazing collision. So, this is another parameter. Then we can define the collision Weber number, which is basically the ratio of the inertial force with which the two particles are colliding to the surface tension force. So, what is this inertial force? This is nothing but the this should be rho d. So, particle density times relative velocity square times average particle size. So, this is basically the inertial force, the force with which they are colliding. Now, this is normalized by the surface tension force, because surface tension will play a significant role when they are colliding. Okay. So, this is called collision Weber number. However, this is true when we have liquids, when we have identical liquids. The situation can be complex if we bring in other factors such that, let us say, the density of the two particles are different. Let us say the viscosity is different, surface tension is different. In one case they have miscible, one case they are immiscible. And also what happens if we have, let us say, higher gas density. Okay. So, you see, then we have to define many other parameters. Okay. And also the size of the colliding particles, they also can affect. So, what is the outcome of binary droplet collision event? So, these are some results which have been obtained by the collision experiment. The collision was made to happen considering two droplet generators, as you can see here. So, you see, depending on the combination of Weber number and the impact parameter, the different outcomes we realize, even if the particle size are more or less similar. For instance, in this case, the impact parameter is close to 0. So, this means that they are more or less colliding head on. So, here you see that they are bouncing, but okay. So, here we are considering, when I say particle, here we are considering mainly droplets. If they are solid particles, this dynamics will be different. Okay. So, in case of liquid droplets, so here you see they are bouncing to each other and then separating. However, you see here that the shape changes significantly. This means that some energy is definitely used in this process, but somehow again the energy is being recovered. But in this case, you see the impact parameter does not change much, but Weber number is now higher. So, now we have fast coalescence. The two droplets are coalescing with each other. There is something called slow coalescence also, where you will not see much deformation in the particle shape. And this is what happens if the Weber number is even smaller than this. Then they will come and coalesce, but the shape will not change much. Then we have something called reflexive separation. So, you see that now the collision Weber number is further increased. Then what happens? They collide with each other, a disk is formed, and then it is separated, and it generates some satellite droplets along with these droplets, these main droplets. This is called reflexive separation. We have stretching separation when the impact parameter is higher, that is, the collision is not head on. So, from sidewise they are colliding, and in this case you see here also we have separation, but it is called stretching separation. Okay. So, they are not coalescing. So, in this case they have coalesced and then separated, but in this case also we see that, but it is a different type of separation. So, here you see what happens. So, here we have basically stretching of the filament which is generated. So, all these combinations are possible, and accordingly people have come up with typical regime map. So, what is regime map now? So, we do this experiment for different Weber number and impact parameter, and we locate what happens, what is the outcome. So, for instance, this line shows, okay, the boundary between, say, coalescence and separation. So, similarly we have drawn different boundaries. Now, this kind of regime map basically summarizes the experimental results into clear visual boundaries between different outcomes. So, it makes the understanding easier. And also, once you have this, then if I give you the value of Weber number and impact parameter, you can immediately find out what is the outcome. This means that we can use this in the models. So, now we can connect this to the model. Which model? Hard sphere model. So, this means that in your modeling, if you know the initial velocity and particle size, then you can calculate Weber number, you can calculate impact parameter and say that, okay, this is what is going to happen. So, you do not have to simulate the entire process. Okay. In fact, this is how modeling is done. So, that is why these experiments are very important. Though there are also simulations of droplet collision, binary droplet collision, which try to mimic the experimental results. So, and people have succeeded in that also. And yeah, so this approach basically simplifies the modeling, because here we avoid expensive interface tracking computations for every collision, and it basically reduces the cost. So, for instance, here you see modeling and simulating all these steps is quite challenging and also time consuming. So, if you do all this, it is not only challenging in terms of getting right accuracy, but also time consuming. So, that is why these maps help. However, the limitations are, this type of maps are basically valid for binary, non-Newtonian, non-turbulent conditions, because the experiments did not account for the turbulent flow field which you always have in a practical application. And these boundaries that we have just discussed, this may shift with ambient gas, temperature, viscosity, surfactants, and also it does not account for three-body collisions which may happen if your loading is high. Non-spherical droplets, what happens if initially the size, the shape of the droplets are non-spherical, or if you have an evaporating system. So, if the particles are evaporating, droplets are evaporating, well, then how would that affect the collision? So, now coming back to the Lagrangian tracking model, so you can do this or you can use this outcome only when you know the probability of particle collision or droplet collision. So, how do we know that? So, there are different approaches there itself. One is the deterministic approach. This means that you actually track individual particles or parcels in your simulation, and you actually see where their trajectories are meeting. So, if two trajectories are meeting, then you say that okay, here I will have collision, and I will use this information of the regime map and predict the outcome straight away. However, this is very time consuming, considering that there are millions of particles. So, if you track the trajectory of each particle and see where they are meeting, then it will be very expensive, computationally expensive. The other approach is deterministic stochastic, which means that you consider the collision only for those particles which are within a cell. So, if these are within this cell, then they collide, otherwise they do not collide. Now, this significantly reduces the computational cost, and here you do not have to track. You say that okay, I have this many particles and they all collide, then what is the outcome? So, while it brings us simplicity and cost effectiveness, this is as expected extremely sensitive to the choice of the cell. So, if you use larger cell, then you have more collision. If you use smaller cell, you have less collision. So, your result or computational output is extremely grid size dependent, which is not good. And also, it does not make sense up to some extent. So, for instance, you consider collision of say this parcel with this and this one, but not with this, only because this is outside this cell. Then we have another advanced approach called stochastic approach, where you does not need to know about the neighboring parcels. So, this is fully stochastic. So, for each computational cell, we use average statistical properties of the droplets that which are needed to calculate the collision probability. So, this is an advanced approach. Okay. So, now coming to droplet collision in sprays. So, this is one example why I have chosen turbulent sprays, because this is a common practical example. So, till now we were discussing mostly binary collision experiment, but what happens in case of sprays? So, mostly sprays are turbulent sprays. Where we face challenge? Challenge is mainly because the sprays are typically polydispersed, means it has wide range of particle size as well as particle velocity. So what happens is that let us say you have a large particle, you have a very small particle. So let us say the small particle is almost like a tracer, let us say. Then when it approaches the large particle, it can just follow the boundary layer and leave without colliding. So then, but your model will give you that it will collide, but it may not. Okay. So these kind of effects are difficult to model. So especially when you have large difference in the particle size. But in a spray, one can expect that why should we expect that only particles of same size would collide? Then droplet turbulence interaction, so prediction of relative velocity. So this relative velocity between particles is quite challenging in case of a spray, a turbulent spray, because it is affected by the turbulence present in the gas flow itself. And we know the common challenges. For example, if you use RANS based model, what you calculate is only the average flow field. You can implement some random walk model, but they are after all models. So basically the bottom line is that you have average flow field, you have instantaneous droplet velocity. Now, if you see, actually it does not make sense, because what do you need is the relative velocity at the same time instant, relative velocity between the droplet and the gas flow at the same time instant, because this we cannot study in a statistical sense. It is an instantaneous phenomena, or this is an unsteady phenomena with very short time scale. Okay, so obviously your simulations will have some shortcoming. On the other hand, if you do DNS with particle tracking, it is computationally expensive. And we have preferential accumulation, clustering of particles. So this also can promote collision coalescence. And there is something called caustic effects, where droplets with high inertia can cross streamlines. So because particles, if they have large relative velocity between each other, so they will cross the streamlines of each other, and leading to large velocity differences, and this can drastically alter the collision rate, but it is difficult to capture in simplified models. And deformation and breakup under turbulence. The particles can themselves break because of the turbulence. So this is called turbulent secondary breakup. This is what happens close to an injector exit. When a particle moves at a very high speed, and if the flow is turbulent, then turbulence can itself induce breakup. So once that happens, then your particle number density changes. Then all your models will suffer, because the models depend on the local number density. So if your simulation does not account for turbulent breakup, then what you predict is wrong. So is the problem. And then, as I mentioned, lack of universal regime maps. So the regime map, what I have shown, it's very useful and it is still used for modeling, but these are for quiescent conditions. Turbulence shifts regime boundaries. Once you have a turbulent flow, the boundaries can shift. But the problem is that unlike that case, we don't have a general turbulent map. So the kind of regime map that I had shown earlier, it does not exist for turbulent flows. And then another important issue is experimental validation is difficult, because experiments themselves are difficult. It is difficult to measure particle size, velocity and outcome, everything when within a spray. You can do this for droplet generator, but within a spray it is difficult to track. Okay. So that is why we don't have enough experimental data to validate the simulations. So these are the challenges. Okay, so finally we end the course here. the course ends, but I hope your journey in fascinating world of multiphase flow begins. And finally, I stop by quoting Isaac Newton's quote, where someone asked him, how much you know? Then Newton says, I don't know what I may appear to the world, but to myself I seem to have been only like a boy playing on the seashore. So he's saying he's like a small boy playing in a seashore and diverting myself in now and then, finding a smoother pebble or a prettier shell than ordinary. So he has found some prettier shell, that's all. Now this is important. While the great ocean of truth lay all undiscovered before me. So the knowledge is still undiscovered. So the applications that you have seen in this course, you can say that these are tip of the iceberg only. So there are much more. However, the foundations are that we covered in the course are very important for you to move forward. So I hope you will be able to model any multiphase, dispersed multiphase flow system that you come across with whatever you have learned. You should be able to come up with a basic model. And you should be able to know which technique, numerical or experimental technique to use to understand. Okay. So thank you.